Look at this fluid dynamics simulation. It's pure chaotic phase noise. Particles are shifting constantly, driven by turbulence, devoid of recognizable geometric order. For centuries, concepts like subtle bodies and chakras have been relegated to the domain of mysticism, trapped in a world of personal experience and metaphor that remains separated from measurable physics. The AE framework applies the mathematics of gauge field theory to bridge this gap, stripping away the metaphors to look at the underlying structure. The framework operates on the assumption that reality is a continuous, measurable, vibrational substrate. To map this, we use the mathematical concept of phase, the precise coordinate of a system within its continuous oscillatory cycle. It tells us where a vibration is in its rhythm. This 3D surface plot shows what happens when phases align. Out of the unstructured noise, a symmetrical peak emerges, indicating absolute structural coherence. By referencing the Cartesian grid and coupling intensity scale, we identify this dynamically stable phase configuration. Our objective is strictly to examine the mathematical syntax that governs these configurations, focusing on their geometry rather than debating their physical mass. This suggests that organized patterns can emerge from a chaotic field solely through the mechanics of phase coherence. To understand how these structures survive, we measure phase entropy, the exact measure of disorder within a system's phase relationships. We parameterize this disorder using a specific entropy dispersion equation. It calculates exactly how chaotic the underlying vibrations have become. Coherence is the structural mathematical inverse of that phase entropy. When the phase relationships lock into perfect alignment, the system behaves as a single, unified wave geometry. This brings us to the biological stability constraint. For any complex system to persist, its coherence must rigorously remain above a critical mathematical threshold. If internal disorder pushes phase entropy beyond that boundary, the system suffers complete structural collapse. A living cell demonstrates this by constantly balancing its highly ordered internal structure against the random thermal fluctuations of its environment. This balancing act is a measurable thermodynamic limit. The equations define exactly when a system holds together and when it breaks apart. Life and functional stability are dynamic regimes, sustained only as long as phase entropy remains strictly bounded. In a highly coherent field, phase gradients organize into tightly spiraling vortices that spin down into dynamically stable central singularities. To maintain phase circulation around a core, it must satisfy the vortex quantization condition. The contour integral continuously tracks the phase gradient along a closed geometric loop. Because phase must align seamlessly upon closing, circulation locks into discrete, quantized cycles, exact multiples of 2 pi. This completed, quantized structure is a topological defect. It is permanent and cannot be smoothed out or destroyed by the ambient noise of the field. In the AE framework, this specific mathematical defect corresponds to the historical anatomical term known as a chakra. This is a mathematically isolated hub of topological information exchange. Chakras are the mathematical consequence of localized phase gradients wrapping themselves into discrete topological locks. This raises a mechanical problem. How exactly do these topological phase nodes exchange data with the physical layers of a biological organism? Transduction operators serve as the formal bridge between the physical and the purely vibrational. We use the transduction efficiency calculation to measure the exact fraction of total field energy concentrated at any specific node. Energy transfer requires a non-vanishing phase entropy gradient between layers, driving the flow of data from high entropy to low entropy zones. Scaling up from individual nodes, we look for how the field retains complex architectural memory over time without relying on physical matter. In differential topology, we use holonomy to map path-dependent change within a curved phase space. Traversing a closed loop in this curved geometry ensures it never returns to its starting state. For memory to persist structurally, the calculated holonomy must never equal the identity matrix. The change is recorded in the path itself. The A framework defines these persistent, non-trivial holonomy loops as reality knots. They function as perfectly self-contained geometric structures, actively maintaining their internal architecture against the constant pressure of surrounding entropy. Historical descriptions of the subtle body, the astral or etheric layers, align exactly with these reality knots. Subtle anatomy consists of path-dependent structural history, permanently encoded into the internal geometry of the field. When we pull back from the isolated nodes, we can observe the integrated configuration of an organism. We map the physical biological layer, the standard cellular networks, directly underneath the topological layer of reality knots and quantized vortices. The transduction operators act as vertical vectors, connecting the two grids. Driven by entropy gradients, they push pulses of data downward into the biological cells. This translates esoteric action into physics, where energy work is defined as the application of intention currents to artificially minimize local phase entropy. By utilizing quaternion ionic algebra, these experiences can be computationally modeled and theoretically tested. The AE framework approaches these phenomena through the mechanics of coupled oscillators. As phase relationships align across the entire system, the synchronized nodes lock into a rigid, crystalline topological lattice. These structural organizations are parameterized by the laws of coherence, resonance, and differential geometry.